In this video, we're going to look at some ideas from Chapter 2. We're going to begin with considering the portions of the periodic table that are describing metals and nonmetals. Then we'll use that information to consider molecules and molecular compounds and compare and contrast those with ions and ionic compounds. In that section, we're especially important in considering the structure, how the particles are arranged, and the composition, the atoms that are present and their representation with a formula. So at the start of the chapter, we begin by looking at various subatomic particles, and then in the second half of the chapter, we're looking at molecular and ionic compounds. In this video, we're interested in different ways of classifying compounds as molecular or ionic and how we might represent them using a formula or some kind of figure or particle representation. In terms of degree of difficulty compared to other ideas within this chapter, this is fairly high up. It's oftentimes challenging to understand what's taking place at the particle level. But if you notice the darker line around it, it's an important idea. We're going to use this again and again. So this is one that is somewhat challenging, but also quite important. So let's see if we can get a handle on it. So if we're considering molecular and ionic substances, we can describe them based on their composition and their structure, the atoms that are present and how those atoms are arranged. For molecular, we're going to be expecting them to be composed of nonmetals, and for ionic compounds, we're going to be finding a metal cation and a nonmetal anion. Metals, nonmetals. If we look at the periodic table, much of the periodic table, the elements are metals. Those are shown here in red. The left-hand side of the periodic table, predominantly metals. The right-hand side, nonmetals. When these become ions, the metals typically become cations, and the nonmetals, anions. Here's the groupings of the charges that they typically adopt when they become ions. So we notice the first column, the alkalis plus 1 cations, alkaline earth plus 2, plus 3 for the column with aluminum, and then negative as anions, minus 3, minus 2, minus 1, and then the noble gases without a charge. So let's add that to our representation as well. Looking more closely, we see hydrogen there on the top left. Hydrogen within this figure at the bottom, there's a representation where it's given a plus 1 charge and also a minus 1 charge. So that's why they grouped it over here on the right-hand side in this example. So let's recognize that hydrogen, even though we're putting it here on the top of this particular column, it's a nonmetal, and it's also novel in that we have both of these charges that we might find it with. When we're looking at the tables showing cations and anions, we see hydrogen listed twice. Hydrogen as a cation and the hydride anion with a minus 1 charge. Also in those tables, we find many polyatomic ions. There's one polyatomic cation and numerous polyatomic anions. The ones in bold, we need to memorize the name, the formula, and the charge. So we can now look at the different substances here and identify them as molecular or ionic based on this characterization here. Are they composed of nonmetals, or do they have a metal cation and a nonmetal anion? So to answer this, you'd want to be able to look back at a periodic table and classify them. Give that a try. Which examples would be molecular substances and which would be ionic? Here I show my groupings. I'm looking simply at the periodic table to see if they're composed of nonmetals, or do I have an example of a metal as well that formed a cation? If we consider their structure, I think this is the part where students oftentimes stumble. We have different representations here. So for the one on the left, this is acetic acid, sodium chloride, magnesium oxide. Let's look at the molecular acetic acid. So within that label, we have the carbon shown, hydrogen, and oxygen. So if we add it up, I see 2 carbon atoms, I see 1, 2, 3, 4 hydrogen, and I see 2 oxygen. So that's what the formula here is describing. The formula is also showing some aspects of the connectivity. We have carbon with 3 hydrogens, another carbon, 2 oxygens and a hydrogen. So the formula is also describing an aspect of the connectivity within this molecule. How about these ionic compounds? Does it seem like the formula is making sense of the information in the same way? For the molecular one, it sure matched up with the picture. It seems like different information is being shared with the ionic compounds. The reason why is because we're using different kinds of formulas. An empirical formula, that's one that gives the lowest whole number ratio of the atoms of each element in a compound. A molecular one is giving the exact number of the atoms of each element. And a structural formula will disclose aspects of the arrangement, the connectivity. Here are our different molecular substances. There's different representations. There might be a picture, there might be a formula, there might be a name. The example there at the bottom for ethylene, we see that it lists the name, a molecular formula, and also a space-filling model. Here's different types of formulas. A molecular formula is one that's telling you the atoms that are present. Structural formula shows aspects of the connectivity. A perspective begins to give you insight into the 3D shape of it. That's something that we'll look at later within this course. And then there's different kinds of models. I mentioned that this was showing a molecular formula. Think for a second, what makes something a molecular formula? I've just introduced a couple different kinds of formulas. Why would you say ethylene is being described as a molecular formula and not one of the others? Here we have a depiction for carbon dioxide. CO2 solid is dry ice, another name for carbon dioxide. If we were to look at this as a solid form, here's a representation for CO2 solid. A couple takeaways from this. When I see this molecular substance as a solid, I see that I have these discrete molecules of carbon, oxygen, and oxygen. That discrete molecule shows up again and again. And there's also a repeating pattern. Every solid has an arrangement that's a repeating pattern. So you notice all of the CO2 molecules are canted to the left, then to the right, then to the left. So a solid is going to have a repeating pattern. Key thing to keep in mind for a molecular substance, that repeating pattern is going to include discrete molecules. They're separate from each other. How about for the ionic compound? So here I show a sodium cation in the center, and it has 6 chloride anions around it. Let's expand that a little bit. Then each of the chloride anions is going to have 6 sodium neighbors. And it keeps going. And that pattern continues again and again and again and again and again and again. And it keeps going. For an ionic solid, you have a repeating pattern, but you never have a discrete molecule. It was always this combination of a cation with anion neighbors around it, and then that pattern was repeating. So which type of formula or formulas are appropriate for an ionic compound? Can you describe an ionic compound with an empirical formula, a molecular, structural? What do you think? Here's the textbook description. It points out that the ions in ionic compounds are arranged in this 3-dimensional structure. There is no discrete molecule, so the authors note that we're going to only be able to use an empirical formula. Does NaCl mean I have 1 cation and 1 anion? It does not. I have a huge number of each if I'm going to put them into this 3-dimensional structure. We're going to be writing empirical formulas, and those match up based on the charge of the ions. Overall, the compound is chemically neutral, so if we look at how many we have with their subscripts, that also gives us some insight into the charge. This would also be consistent if we look back at the periodic table. Magnesium is in a column to make it a +2 cation. Nitrogen as a nitride 3- anion. So if I have +2 times 3, that would equal -3 times 2. The overall compound is neutral. So we have some insight into the being able to describe the composition for molecular and ionic. We analyzed the formulas. We considered the structure. How about something like F2? What's that going to look like? F2 is an example of a diatomic molecule. There are 7 elements that occur in nature as molecules containing 2 atoms. So I need you to memorize those diatomic molecules. Elemental form for hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. They're all diatomic molecules. Here's a representation of how a molecule exists in different states of matter. This would be a water molecule, if it was a solid, if it was a liquid, if it's a gas. Notice in each case, we preserved the molecule. We had a discrete molecule. We were just changing the spacing on them. We were changing the potential energy. Here we see oxygen as a solid. So it's at a very low temperature. Oxygen is one of our diatomic molecules. And sure enough, we can see that we have many, many O2 molecules that are stacked up. So what do you think an element like hydrogen, nitrogen, bromine would look like at the particle level if we turn this into a liquid or as a gas? This is a solid. What do you predict it would look like as a liquid or as a gas? Here we can explore it. So I'm taking diatomic oxygen. If we begin to add heat to it, we see the molecules are jiggling, but they remain as diatomic molecules, whether they're a liquid or whether they're a gas. Okay, how about something like MgBr2? What do you think that structure looks like? It seems somewhat like we're combining different ideas. What's your take on an ionic compound MgBr2? Share your ideas. What do you think that would look like at the particle level? Here's a depiction of MgBr2 at the particle level. Recall that for an ionic compound, and MgBr2 is a ionic compound, we're going to be using an empirical formula. We're going to have a pattern that repeats again and again and again. So it turns out we would have magnesium with 6 bromide ions around it, and each of the bromide turns out has 3 magnesium cations around it. Those particular ratios are not something, as far as how many specific neighbors they have, I'd expect you to know. But importantly, we want to see that this is an ionic compound. We don't have bromine Br2 molecules present at all. This is just another way of saying we have 2 of the bromide anions. How about this end of chapter question? Which of the following diagrams most likely represents an ionic compound, and which one represents a molecular one? Share your ideas and give your rationale for your prediction. Here's another end of chapter question. It says the following represents an ionic compound, with the blue spheres as cations and the red spheres as anions. Which of these compounds would be consistent with the drawing? As I look at it, it looks like the ratio is for every 1 anion, I have 2 cations, and it's an ionic compound. Which of these formulas would match up with that? Give that one a try. So in this section, we've been exploring molecules and molecular compounds, ions and ionic compounds. We spent some time talking about the composition, the atoms that would be present, different formulas that we can use, and then different representations for how they are arranged at the particle level.